So yeah, let's see what's recap. So what I did in this, I was hoping to convey in this tutorial is I gave you very basic introduction to the standard or the classic questions that we're looking at in machine learning theory. In particular for binary classification, and of course this is just very small subpart of the type of problems that machine learning is addressing, and that therefore machine learning theory is attempting to analyze and to give guarantees for. So what we've seen is this basic principle, and we've seen that playing out in various fields. But the basic principle is that we need to or what we're aiming for is some sort of control over the performance of the output of some machine learning mechanism. So if we fit some sort of a function to a data set, the main question is, does this function only capture the particular patterns that we see in the data set, or does the function that we fitted actually capture an underlying trend? And what can we do to ensure that our machine learning mechanism is not overfitting to a particular data set, but instead reflects the underlying data generating process? So we've seen that playing out, in the kind of the standard framework of binary classification. So the classic analysis there is the Vapnik-Chevonenkes, or using the VC dimension. So I've showed you even the proof of how bound VC dimension for hypothesis class leads to generalization guarantees. And what I was hoping to convey there is really this principle that what the VC dimension is capturing, or what it is quantifying, is how flexible the class of predictors that we're using is to fit itself to the particular patterns in the data set. So the fact that we saw Sauer's lemma, the VC dimension restricts the number of behaviors, the number of possible patterns that the class can induce in any particular data set of arbitrary large size. So we saw that once the class is bounded VC dimension, then the number of patterns that it'll induce on any data set grows only polynomially in the size of this data set rather than exponentially. And this particular effect, so I've shown you also technically how this actually lets us derive generalization guarantees. And this basic principle, it plays out in various forms just for the binary classification task. So I've mentioned a few other techniques without having gone into details. So for example, there's compression. So I mentioned there is an analysis of whether we can compress patterns that come from a function in the class to a number of, to a bounded number of, or bounded size subsample for any sample. If that is the case, then again, the function class can only induce a polynomial number of patterns on any data set size. So we get generalization guarantees essentially for the same reasons. And then this compression idea can not only be applied to hypothesis classes, but it can also be applied to algorithms, to learning algorithms. So if we can encode the behavior of a learning algorithm, if that only depends on a fixed bounded number of sample points for any data set, then again, the algorithm's flexibility to overfit is restricted in that same way. So we can use this compression idea also to actually analyze learning algorithms rather than classes of hypotheses. And then there are various other techniques that capture this phenomenon in more fine-grained ways. So Rademacher complexities, it essentially captures the same thing, but has a little bit more of a potential to have a more fine-grained analysis there. Or algorithmic stability, again, is the same idea. There's this idea that if the output of a learning algorithm cannot change too drastically if I change one point in the data set. Either I take one point out, or I replace one point with another random sample from IID sample from my data generating distribution. If the output of my algorithm cannot change too drastically, then again, we can use this fact in order to derive similar generalization guarantees. So all these techniques, they somehow revolve around this similar theme, that they somehow they reflect regularization that is either inherent in the class or in the learning mechanism. So that was the basic idea that I was hoping to convey with the first two lectures. And then in the last lecture, I was talking about transfer learning, domain adaptation, and essentially sending a similar message, saying we need to incorporate prior knowledge about the learning tasks. So in a standard setting, that would be by the choice of the algorithm or by the choice of the hypothesis class that we're attempting to use. In a transfer learning, that would come through. We need to have some sort of idea of what type of change is happening, and then choose an adapting learning mechanism, so a transfer method accordingly. So so again, the message there was, for any particular transfer method, there will be a kind of type of change that this method will fail on. But once we have some sort of idea of what is actually, what type of change may be happening, there are also actually successful techniques. But yeah, the main message is that we need to, we shouldn't expect magic from machine learning, although sometimes people these days tend to do that. So I'm a little bit on the pressing the brakes here and saying, don't suddenly start believing in magic. But what I would like to promote is to really try to understand how these learning methods work, do the work of getting a little bit into the mathematical underpinnings, and then what I would hope that will be achieved with that is that we can derive a better matching of learning methods to learning tasks. And I think there's still lots of work, also lots of research work to be done. It's a very exciting field. So I was hoping that I, at least to some degree, convinced you that machine learning is really a field where theory and practice are influencing each other in very fruitful ways. So over the decades, we've seen that it's sometimes the theory really driving the development of practical algorithms. Sometimes it's more the other way around, that the practice is successfully running ahead, and the theory community is trying to understand what is actually happening. But I believe that both parts are really crucial and are playing well with each other. So so I think it's worthwhile to have both the practical developments and selling off exciting successes, and then also have a part of the community that says, well, let's try to understand when do these things actually hold, under what conditions. Can we make this precise so that it's actually going to be reusable for other people in the future? So that is my brief recap. I'm really happy to answer any questions or hear from the students. I'm actually also curious how did you students how did you get into this field? What excites you about machine learning? What brought you into this field?
Yes, we have quite some questions already, so I will start with one that is maybe more of so we are now in a world dominated by deep learning, and so do you see that ideas such as PAC learning, so probably a person correct, are they still relevant, or should we just know them for historical reasons and to broaden our mind?
I think I think it's relevant to understand what type of guarantees we can shoot for. That's why I always, I kind of pay attention to, what kind of order of classifiers, order of quantifiers in these statements. I think it's very useful to understand what we're really claiming with these methods. I wouldn't say that, of course, I mean, I guess I said that, right? The VC PAC type of framework is not what is going to explain the success of deep learning methods, but it's important to conceptually understand what we're actually claiming when we say, oh, deep learning is so successful. And to have kind of a, I would say kind of a logically precise framework to state these success claims, and also having these techniques available is just for any particular researcher, if you want to do research in this area, then having these techniques in your toolbox is important to make progress on the more say modern problems. So I think it's important both to for setting your frame of thinking of what do I mean when I say something converges. So that's also why I did these two exercises in the beginning, right? So we tend to say, oh, as we see more and more data, and then everything will converge to success. So I think it's important to have clean framework in your mathematical toolbox to make precise statements, and then also to develop the techniques that can lead to guarantees for deep learning methods. You will very likely need to know the basics. Now I don't hear you.
To this, is probability theory the right tool to assess the generalization ability of the complex ML methods such as neural networks, or should we look to other fields, other concepts?
Is probability right? So yeah, what is probability theory? That's a good question. I mean, to me, probability is it's somehow our mathematical way of phrasing uncertainty. I don't know a better way. I mean, there's of course, there's for example online learning framework, right? That is just looking at sequence of of tasks. So I think it's good to ideally have all these toolboxes ready for you. But it's one way of phrasing of having a sound framework to phrase uncertainty and also phrase that data generation is somewhat stable. It's not at least before we were in this setup where there's really adversarial manipulation. Nature, we were assuming, is not adversarial, right? So I do think that probability theory is the right way to model this mathematically. Of course, if you want to understand these methods and if you want to derive guarantees for them, I mean, there's many other subfields of mathematics that are relevant for that, right? You need to know linear algebra, you need to know optimization. So I think probability theory is one way of soundly phrasing these type of questions and giving answers to them.
Yes, and have you seen?
Not the only one, yeah.
And connected to this, have you seen tools or ideas from optimization theory that consider optimization process as the process of model selection for a specific data set?
Have I seen optimization as the process of, so I think, I mean, if we only optimize, right? I mean, to me, this is really, I mean, to me, machine learning is exciting as kind of the combination of the statistical like probability theory and optimization aspects, right? So it's really this field of asking how do these things play together? It's not just statistics. We maybe have some, fixed generative models are asking, specific statistical questions about them, but we're really asking how does the optimization, the algorithmic aspect, how does it interplay? How does it affect what we're seeing statistically? So to me, this machine learning is really the field where we analyzing how these two algorithmic and statistical aspects come together. So I don't see how or why we would just completely kick the statistics out. I don't think that would reflect well what we're actually after. I mean, optimization is somehow is kind of a tool to algorithmically derive at the output of some you know, input is data, and then we do some sort of optimization, and then there's an output. But if we want to talk about the performance of this output, we have to have some kind of framework in mind to phrase the success of this output, and I don't see how purely optimization would, you know, provide a framework for phrasing that.
And have you seen, for example, so we have busy complexity, Rademacher complexity. So are you familiar with new approaches that can be used to define the complexity to estimate the generalization bounds for neural networks?
I mean, what I see is that, you know, different research areas, you know, everybody throws their favorite tool at this problem, and then comes up with various conclusions, and, you know, hopefully eventually we'll see some kind of you know, pattern emerging. So you know, I think it was, you know, clear relatively quickly that, you know, VC theory is not going to solve the issue of deep learning. So I've seen people looking at it from a compression perspective. There's some work of Shai Shalev-Schwartz, also Sanjeev Arora, who have looked at this problem through a compression perspective. There's work that has looked at this problem through algorithmic stability. Some were arguing, I mean, the optimization method that we're most of the time using in machine learning, especially these days, is stochastic gradient descent, right? So we are optimizing using gradient descent methods, and one can of course look at specifically stochastic gradient descent. What is this actually an algorithmically stable method, and does the generalization actually maybe come from that? So that was something that was people were hoping to see answers from maybe for a while, and then came this study that I mentioned briefly on Tuesday, where they permuted the label on I guess ImageNet data, and then turned out even if you use the same model and the same algorithms, sometimes it generalizes, sometimes it doesn't generalize. So it can't be just the algorithm or just the model. I mean, the third aspect that I haven't mentioned so far is, of course, somehow kind of a smoothness or a naturalness, whatever that means, of the actual data generating process. So nature is not permuted labels. So I think what we will see is that, you know, somehow this third aspect will have to come into the picture, and will derive guarantees to that. And I mean, that has been done, you know, very early already for, you know, I mean, the earliest guarantee, the earliest, you know, type of learning bounds that we've seen is not what I mentioned. I even left that out in my historical overview, but in the 60s already we were, people were analyzing nearest neighbor methods, right, and showing universal consistency of nearest neighbor predictors. And this, you know, if we want to have finite sample bound for nearest neighbor predictors, this always goes through, so these are also very flexible predictors. I mean, they're not computationally efficient, but in terms of their ability to adapt to flexible to complex pattern, of course, nearest neighbor is very flexible, and there the analysis usually goes to assuming some sort of smoothness, some sort of benignness of the actual data generating process. I mean what I like about the people tend to say, oh, pack learning, that's maybe, maybe that's old fashioned. Why are we even talking about that? What I do like about this framework or this type of guarantee is that it, to me, it has, it fixes the right things. So what we have control over when we are doing, when we have some machine learning tasks and we're choosing an algorithm, we're choosing a hypothesis class, these are the things we choose. The data generating process we have no knowledge of, right? So I think what is nice in the PAC framework, and I think at least it's worthwhile, trying to keep this aspect alive as much as possible, is this aspect that we that what goes into the bounds is the aspects that we have control of. We have control of the hypothesis class, so we have control over what VC dimension or whatever other complexity measure we choose we are using. Whereas the data generating process, what is the smoothness of the data generating process is something we don't know, right? So I mean, once we start deriving bounds that involve the data generated aspects of the data generating process, essentially we're giving bounds that we cannot evaluate because we don't know what nature is. I mean, that's the whole point, right? We're doing learning because we don't know what's the smoothness of the data generating process. I think we will probably not, not be able to fully avoid that. But I think it's good to have this, at least this aspiration to have this, keep this in mind, that this was actually is kind of a positive aspect. I mean, at least in my eyes, of the PAC framework, that the bounds involve parameters that we have control of, and give universal guarantees over the the set of things, namely all distributions, which is the kind of the aspect of this whole problem that we have no control of.
And now that you mentioned so stochastic gradient descent, are there results connecting the classical generalization bounds with models found by using stochastic gradient descent?
Yeah, there are. So there is. I think one of the first studies in this direction is also now maybe 4 or 5 years old. Also Moritz Hart and so there were. I mean, what I mentioned already, that the initial attempts of analyzing stochastic gradient descent through the algorithmic stability lens. So that is one work. I can try to find the reference. It's Moritz Hart, and I don't know if it was also Ben Recht, this type of group, and their follow-up works. Nati Srebro has lots of work on analyzing stochastic gradient descent, and the generalization properties that come out of that. There is work in that direction. Often, I mean, often the actual guarantees that we have there are still for problems that we already kind of understood before, maybe just not through stochastic gradient descent. So maybe we have better analysis of stochastic gradient descent for linear predictors. Linear predictors we understood before. So I think there's still, at least as far as I'm aware, there's still quite a gap between these types of analysis that involve the optimization, that involves stochastic gradient descent as the optimization, but actually applying them to the type of models that we see these algorithms apply to, and so really huge neural networks.
And what are the practical implications of the VC dimension?
What are the practical applications? Implications. That we understand what leads to it's the same as for all these other techniques, that we get an understanding of what how model complexity interacts with generalization of a machine learning process. I don't think that these bounds are there to take them and somehow turn them directly into an algorithm. That's somehow not the point. The point is that we have conceptually gain understanding on what will lead to overfitting, what will lead to underfitting. What it's a sound frame on what type of guarantees can we hope for.
And can you share the intuition on how to compute the complexity of a classification algorithm using VC dimension?
So I don't think there is, a general technique, and if you define, throw some complex. So there are some classes where we understand what the complexity is, but it needs, essentially it needs a different analysis for each class. It's for each class. There's no universal technique as far as I'm aware of. We understand. I mean, the typical knowledge, of course, people have looked at, so we have some understanding. So we know what does the VC dimension of various linear or various, neural network classifiers. What does it depend on? Decision tree, majority votes, so forest, random forest. I mean, these type of things we have some understanding. So there's, people have looked at this and provided some bounds. But there's no, as far as I'm aware, universal technique that, the algorithm that, if you throw a hypothesis class at it, it'll compute the VC dimension.
And what are the assumptions in ERM that we can ignore?
What are the assumptions in so ERM? So ERM is somehow, it's not it's kind of a principle, right? As a principle is, we want to, it's essentially what we typically do. We do some sort of risk minimization. I mean, what stochastic gradient descent is typically doing. I mean, once you decide on some loss function, it'll attempt to find a model that has a minimal risk with respect to this loss function. Right, so it's not an algorithm, it's a general principle. Typically, it's combined with some form of either explicit or implicit regularization, right? So typically, we wouldn't just want to look at empirical risk minimization, but some sort of regularized risk minimization. Yeah, I'm not sure what is meant by that we can ignore. There is a whole issue, of course, that ERM is ERM, pure ERM is for most interesting classes just computationally hard. And then what we do is you will rarely see a method that will actually attempt to, for example, minimize the 0-1 loss directly. Typically, what we do is we use some, surrogate or some other loss functions that have more of kind of a convex behavior, and maybe at least for linear classifier we would get a convex optimization problem, and optimize these functions instead. So it's also something that's good to be aware of, that typically we what is actually done in practice is not even optimizing the loss that we in the end actually care about, but we optimize some surrogate loss function for computational reasons, or it's actually also it's kind of again a combination of computational and statistical aspects that would promote the use of surrogate loss function. But then, of course, overall, you'll have to look at there's various sources of errors that come into the whole picture. There's how well does the minimizing the surrogate loss function, how well does it actually reflect optimizing my actual loss? How much of a mismatch is there? How much am I actually able to minimize the surrogate loss function? There's an optimization error that comes into the picture just from the optimization essentially being computationally hard. So we use all kind of approximation or just heuristic approaches to hopefully find some minimum. So how far off are we? How far off are we from what we find? Is it from the actual minimum of our loss function? And then how far is this off from the minimum of the loss function that we would actually care about, like in binary classification? I would argue that really what you want to minimize is just a number of mistakes, but you would rarely see a method that will go for optimizing that. So there are several steps of mismatch that I think it's at least good to be aware of them, and then as things go wrong, one can start looking which of these kind of connections was actually causing the problem potentially.
And if we talk about generalization error bounds, are there ideas how to select the model complexity for a specific data set? Have you seen cases where it has been successful, and how has it been used?
Yeah, so I mean, so what I didn't, I mean, because this was very basic, right? It's just 2 lectures. So the next step would have been to, talk about structural risk minimization. So structural risk minimization says, there's, say we have kind of a hierarchy of models, and then, it gives us bounds on, balancing out the complexity of the model class and the, the approximation capability of this model class, right? So there are bounds that, involve this balance. And many of the the bounds that we have for for regularized loss minimization methods, I mean, they essentially do exactly that, right? So there's this balance between the regularizer that measures model complexity and the empirical risk, right? So any kind of analysis that you see for regularized loss minimization, they essentially they have this model selection component built in.
And maybe you can say some words about algorithmic fairness and how it connects to learning theory and the ideas that we have seen in the past couple of days.
Right. So algorithmic fairness, I mean, this is kind of a whole new, kind of type of issues that come with algorithmic fairness, right? So, so one thing I can say is that the type of guarantees that I was talking about, if we just optimize accuracy, then it this is not suitable for also taking fairness into account. I mean, very simple example is I can get a if I have a minority group, say that maybe has, I don't know, 3% of my population, and I shoot for accuracy 5%, then I can just completely misclassify all of the minority group, right? So just shooting for accuracy will not automatically balance how well am I doing on various subpopulations. So that's also, it's good to be aware of, so that if we wanted to, if we have certain, say, protected attributes that that divide our population into various subgroups, and we want to make sure that all these subgroups are treated fairly or treated equally, then one has to make an additional effort. So much is clear. And then of course there's there's lots of work in recent years that we've seen. So what is actually what is a suitable notion of fairness? Where does that come from? How can we achieve it? There's lots of very interesting questions that one can ask, and debate the notions that should be in use. And I think that's what the community is doing. It's now there's no right now commonly agreed upon phrasing of fairness, and there's different notions of fairness of predictors that that contradict each other. So there's again this theme that whatever you will we need to understand what we're doing, and we need to choose what we're doing accordingly to different according to the situation that we're in. So we'll always have to think about how does what I'm doing actually match with a particular situation and with what I'm trying to achieve in this situation. So that's again, there will be this no free lunch message for me that we have to. There's not going to be kind of a solution to make machine learning fair. Yeah, I think, I mean, the basic thing that's important to be aware of is that different notions that we would intuitively think maybe this is what we should aim for in terms of fairness, they contradict each other, and really which one is suitable will depend on both your worldview and the particular problem that that is at hand. And again, I think our role, I mean, I would see my role as a machine learning theorist, making this transparent, right? Making it clear that there are these different options, that they might contradict each other, and which option may maybe provide kind of formal understanding for which option may be suitable for which characteristics of a certain situation.
And what if we reduce the dimensionality of X with a classifier of source versus the target data, and then estimate the densities and the ratios? in the one-dimensional space of such classifiers' output?
So the idea is to say let's project both source and task to a one-dimensional space and estimate the density ratios there.
Yes.
Right, but then you'll depending on how you project, right? There's many different directions, many different one-dimensional directions in space that you can project onto. You will get very different density ratios depending on your chosen direction, and then you have the issue of what is the right direction, and I mean, this is essentially what is happening if you do linear classification, then you're projecting everything on a one-dimensional space and do a threshold in this one-dimensional space. That's what a linear classifier is. So if you're lucky and so I would need to think about. I mean, my spontaneous reaction would be is that this is probably oversimplifying, and there's lots of situations that you will not catch with such an approach. Maybe there are situations where that will work, but I would think that in many situations, definitely as soon as the problem is not linear, this will not give you useful important weight in the original space.
Mm-hmm. And for someone interested in learning more about learning theory, do you have any books, surveys, or recommended literature?
Yeah, so my, let me, 1 second, I'll just go here to my bookshelf. So this is the book that I'm, sorry. Can you see it? So this is Understanding Machine Learning from Shai-Shalev Schwartz, Shai-Ben David. I think this is a very nice book in terms of, getting kind of a sound, but also intuitive, basic theoretical understanding, and also, seeing some of the algorithms that are developed. How do they connect with the, which type of tools can we use for which type of algorithms? Which kind of theoretical tools can we use for which type of algorithms? And it's not, I would say it's not too mathematically heavy. So I think it's kind of a very good balance of, talking about algorithms and various techniques in theory without being too heavy on either side. So that's what I would recommend and it's you can go to Shai-Shalev Schwartz. If you go to his website, the book is legally available as a PDF, so has been since the beginning. So it's available to at least in PDF form to anybody who's interested.
Yes, and if someone is interested in working with you, so what are you looking for in a collaborator or a student, and also how can that person reach to you?
Right, write me an email. I'll definitely be happy to connect with students or also potential grad students. I mean, we're hiring grad students every year, right? What I find important is kind of a basic willingness to understand, to really go into details and develop formal understanding. I mean, this is what my research is, right? So I'm not a machine learning practitioner, and I don't think I'm not planning to morph into one anytime soon. So it's basically curiosity and ideally kind of a sound mathematical background. Ideally, maybe in having studied math is definitely appreciated. So enjoying mathematics and enjoying asking these type of questions, I think that's what's most important.
And are there ideas in machine learning that you find underrated and we should be paying more attention to them?
And the field is so large by now. What should we pay more attention to? I mean, I'm really interested in these, I'm interested in this aspect and how can we translate between the formal and the technical world of these applications and users that maybe don't have all the mathematical and all the technical background. How can we develop languages to convey kind of the important technical aspects or decisions that have to be taken So we don't just try to sell magic, right, and say, but if you have a problem, these are the 10 questions maybe that you should ask, even on, and somehow phrasing these in a language that will not require having studied optimization or having studied statistics. So how can we do this, and how can we do this in a kind of a mathematically sound way? So I'm very interested right now in these questions of transparent interpretability of machine learning, fairness, and of course transfer learning, different aspects of transfer learning. What type of guarantees can we give, and how can we communicate them?
And do you have any advice for female researchers starting their career now that there is so much discussion on so the place of female researchers in the field? Any thoughts and recommendations that you might have?
Yeah, if you enjoy it, if you enjoy the field, then go for it. I'll be happy to see you. I mean, I'll be happy to and seek out seek out mentors. Come to we're organizing lots of these days, lots of events for seek out your peers. So I mean, I want to acknowledge that it can sometimes feel lonely, right? I mean, if you're in if you're the only student in a large at a university in this really minority situation, it sometimes can feel lonely. But as soon as you get to conferences, there are events, connect with other people, and go for it.
Can you share with us how you got started in this field?
How did I get started in this field? So actually kind of by by accident. I studied mathematics. I loved mathematics. I studied mathematics and philosophy. Actually, I got into computer science relatively late. But yeah, I was in love with mathematics, and then at some point thought, okay, maybe I want to do something that is not fully abstract and a little bit more, doing mathematics on topics that I can also explain to friends and family. So decided to go for PhD in computer science, or in theoretical computer science. And then it was really through my advisor, through Shai Ben David. He's also a mathematician and was just very good connected. And then he turned out to be working on learning theory. So I worked on learning theory, and now I'm fascinated with this field. So it was really through my interest in mathematics, and then just an opportunity. Of course, that's also, now 10 years ago, easily, if not more. I suspect that now people, maybe these days get, maybe interested in machine learning earlier, because the field is just so visible and so influential by now. But for me, it was really through my love for math.
And as a last question to conclude, for anyone starting, which ideas, research directions, or concepts should this person look into? What should be like a good direction to get started as a researcher in machine learning?
Yeah, I think as a researcher, I would really recommend, so there's, of course, one aspect, you have to kind of enjoy the general, say math, computer science, or engineering type of, problems, and, and then I would really, I would not so much recommend, try to figure out what is the right, because, and as a student, this is not something what you can easily have a good idea of, but really try to find mentors, try to find, successful researchers that, are working on interesting problems to you, and are also, somebody that you can work with well. And then, yeah, get good advice, get good guidance. I think it's very, very difficult as a student to, decide on your own. There's some people that, just do their, know the direction, but it's very, very few people, and most people will be successful if they're in a kind of supportive and good advice environment. I think it's very important to be have a group of people to work with that you work with well, and to have a good advisor. That will,
Great. Well, we have already covered quite so many questions here, and as I understood, there is interest from the audience to contact you and explore possibilities to join your group. And
definitely, yeah, contact me. I'll be very happy to hear from you.
Great.
Yeah.
And well, we have, even though it was introductory, I am sure that this provided a good overview for the audience on what is happening in the theory of machine learning. It's quite different from other sessions that we have had that were much more applied. And this brings a good mix into the table. So for that, thank you very much, Ruth. We're happy you could be part of our school.
Yeah, thank you. Thank you for having me. Thank you for inviting me to the school. It was a pleasure to participate in these sessions.
Well, then, with that said, thank you very much and have a nice day. We're looking forward.
You too. And have a good rest of the school. Learn lots of interesting stuff.
Hope that will be the case.
Yeah, thank you very much.
Bye.
And feel free to reach out. Yeah.
Bye. We will, yes. Now, for everyone, we're about to start with our next speaker. He will be talking about NLP. We have not really covered NLP during the school, so it'll be very exciting. And yeah, so it will start in about 10 minutes. So we'll have a short break. And at 5 p.m., we'll have our next speaker on NLP.